Hello everyone again, and welcome to this particular video where in here we're going to be continuing from where we stopped, involving the Heck reactions, and specifically we'll be looking at a specific path of this cyclic reaction called the beta-hydride, and there is a form that actually leads to a more stable process, which is the formation of a stable product. And in this video we're going to explore the reverse methods that actually occurs in target reactions that leads to stable products. So in this case here, we will first actually focus on the big idea of the Heck reaction, where first off we begin with the oxidative addition, where we have our organic halide that actually creates a complex with a particular palladium 0 oxidation state in order for it to increase its oxidation number to +2. Therefore, we have a palladium +2 that is formed when we have this complex created, and then by carbon metallation or either some methods where we have migratory insertion, we have a specific sigma bond that is not actually created in this step, but first there is a pi bond that actually interacts first with that particular complex metal region, and by so doing this actually leads to the formation of a carbon palladium bond, and that actually then results in a next process which is called the beta-hydride elimination. And in this case what happens is that we produce our product, and this particular pathway, which is the beta-hydride elimination, is what we're going to focus mainly on in this particular path. And then finally we go into the final step involving reductive elimination, where we reproduce or regenerate our palladium 0 catalyst that continues in that cycle in the presence of a base. So in this video here we're going to explore mainly the beta-hydride elimination and explore the beta-hydride elimination product favorability, and how this is not only enhanced in terms of the right base, but also how the specific segments of your halide or organic halide or olefin influences the formation of our product. So in here we're going to look at what is reversible. In this case we have the beta-hydride, that is the elimination that is reversible, and this reversibility actually is applied to this particular case scenario where we have our orange compound, which is the organohalide. We can actually identify that with the X, which represents any halide or triphthalate, but we won't talk about the triphthalate yet. We'll talk about that on our next video, so watch us for that. And that particular pink color compound represents our specific olefin, or I might call them the specific double bond alkene that is going to be involved in the next step, which is called the carbonmetallation. So in the presence of our catalyst, which is palladium starting with oxidation state 0, and in the presence of a base, what is the major product of this specific reaction here? Now looking at the mechanism here, we are going to first start with palladium 0, and palladium 0 could have various ligands that are involved in a way in terms of ligand exchange, but it still maintains the oxidation state of palladium to be 0. However, once we introduce our organohalide, our organohalide causes an increase in the oxidation number of palladium, where in this case, due to the process called oxidative addition, we actually create the formation of this complex, which has palladium to go from positive or 0 of course to +2. Now the next step, which is carbonmetallation, is where we introduce our specific double bonded carbon. We notice that this compound here is a form of an alkene alcohol. There is something quite unique here because there is of course an attraction between the double bond and the palladium, and this actually leads to the formation of our palladium carbon bond. But what you see here is that there is a formation of a carbon-carbon bond around that region in that case, and also we see that the position of this particular orientation of the double bond to the palladium is not in the opposite way, where we have the oxygen pointing downwards relative to that specific palladium, where in this case we won't have an unfavorable formation or reaction due to a process called sterics, because we have a Boyke group that is pointing in the same direction as that of the Boyke group on that particular complex. So therefore this particular process is unfavorable, while what we did in the first process there, which leads to the carbon methylation, that is successful, to be favorable. So moving on to the main cycle in this particular step, the next step is called the beta-hydride elimination, and in this particular step we know that we need to pick one carbon that is beta to the alpha carbon, and that hydrogen will have to leave. Now the big question is it this particular hydrogen here, A, or is it hydrogen B? Now this comes into play choosing when we actually decide on which one will form a more stable product, which means which one it has more resonance effect and which one will lead to a more stable conjugate base, if you think about it in that particular manner. And what we see here is that hydrogen B actually produces a more stable product than that of hydrogen A. And you might be wondering, why is that the case? Why is that the case? If you look at the instead case where we pick hydrogen A as the beta-hydride that will be eliminated, this actually causes the formation of a double bond to be further away from that oxygen. Therefore this will lead to an unstable product because there is no form of double bond formation that will relate with closely to the oxygen. However, if you look at it in the other way, which is a proper way where our hydrogen B is actually going to be eliminated, we actually lead to the formation of a double bond carbon-carbonly that is closer to the oxygen. Therefore we create an enol, and this enol will further be influenced by the base, and once a base is introduced we actually lead to the formation here of a product which is called an aldehyde, and this is actually where we actually create a more stable product in this particular method right here, and by reductive elimination we get our palladium back to its original state, which is called the palladium 0, coming from palladium 2 with the presence of a base. So therefore, in conclusion, the beta-hydride elimination is reverse of course, and this actually by introducing our two main reactants in the presence of palladium and a base, we need to form a product due to that particular step, beta-hydride elimination, that will have not only less sterics but also an increased resonance in the product end. Therefore we will rather produce an enol in here that leads to an aldehyde compared to the other instead step where we couldn't achieve this particular product but rather create a more sterically influenced side product that is not really favorable, or a side product that has less resonance. So that's about it for this particular video. Hope you're able to explore and understand how beta-hydride elimination is really key and important in creating a more stable product due to obeying resonance and also less sterics. And on our next video we will focus more on other pathways within the Heck reaction that actually improves a specific stereochemistry to that particular products that is created. All the same, please don't forget to follow this particular channel by subscribing and also hit the like so that others can actually get a chance to check out these videos, and you guys will be able to not lose track on any videos that are coming up in the future. All the same, stay smart and always believe in yourselves.